Hi guys, in this case, we're now just going to look at what is happening this side. Well, the question is now telling us to say that two of the vehicles which were supporting this system have been disconnected and we now only have one car, but it has been loaded extremely and the engine is off. But want to find what its mass has to be if the system is going to remain in equilibrium. Well, this perhaps is going to be the easiest of the three questions we've done so far. So picture the car as if it was just an object like this. And the question is saying that this is supposed to be in equilibrium. So if it is going to be in equilibrium, what does it imply? Well, it means that, okay, I'm going to draw a straight line. It implies that the tension in the rope to the car, the tension that we just from calculating there, the actual tension. So we're taking this to be a build up to say we started with the 3 pulleys working very well, then we moved on to 2 pulleys dead, and then we found what the tension was. So we're going to use the tension when the 2 of the pulleys are not working in this system. So in this case, tension to the car will appear as the force trying to drag the car backwards in this direction. But then in this case, since the engine is off, the only thing that will be holding the car in position will have to be the grip between the car tires and the ground, which is friction. This implies that friction will have to go backwards in that direction. Okay, so if this is to be in equilibrium, or if the bridge is supposed to maintain its position there, it means that the condition of equilibrium, sum of forces equals to 0, must be satisfied. Force of friction is to the right, so we'll take it as positive. The tension is to the left, to take it as minus, but the two have to be equal. So the force of friction has to be equals to T. And in this case, when you look at the forces in the vertical axis, we will have the weight of these objects going downwards. That's the car plus the load. That is going to be mg as the weight. And then we're going to have the reaction force, the normal from the ground, acting on the car. So of course we know to say that it's going to be the normal will be perhaps on each wheel, but to take the overall one acting on the car altogether. So regardless of where we put it, we won't go on to evaluate the rotations here. We'll only need summation of forces. So in this case, we can even say right on the middle. Regardless of where we put it, this math is going to come out. So we're going to have the normal there. So of course, we came up with sum of forces in the horizontal axis, ended up with this expression. And then of course here, we know what T is. It's the tension when 2 of the pulleys were dead. We just from calculating this and assuming of course that all the math here was correct. So we're just going to use this value. And this is what we're going to have here. So force of friction that the car is supposed to experience will have to match whatever this is. So this is in kilonewtons. Now, when we sum forces in the vertical axis and say equals to 0, there are 2 forces. The normal goes up, positive. The mg goes down, negative. This is equals to 0. So the normal has to be equals to mg. Now, the mass of the car is what we are looking for. G, we know what it is. Let's take G as 9.8. So that is the mass there. Now, why do we need this normal? Well, we know that force of friction can be connected to the coefficient of friction. So in this case, we're going to have the coefficient of friction is force of friction divided by the normal force. Or this implies that force of friction is equals to the coefficient multiplying the normal force. So we already know that force of friction has to match the tension. So we can just say that, okay, since force of friction has to match the tension, we have this, but this now has to be equal to the coefficient multiplying the normal force. From sum of forces in the y-axis, we did find that the normal force is the same as 9.8 multiplying the mass of the load, that's the car and everything else inside. And then from here, the coefficient is the only thing that we now need for this to actually work out. So the question did give us what the coefficient was. So if we go back to the values, where is that? So let's see. There we have it. So between the vehicle tires and the ground. So yeah, that is what they're giving us there. So in this case, they're saying the coefficient of friction between the vehicle tires and the ground is 0.79. So we're just going to get this value, and that is what we're going to use in that calculation. Then we have everything that we need. So let's wrap this one up. So the coefficient is this. We plug it there, make m the subject. You'll see that the mass of the load and the car altogether will have to be equals to That's 17,644.937. This, don't forget, this is in kilonewtons, but we're dividing this by 9.8 by the coefficient 0.79. Now, instead of kilo, we want to get, if I want to get the mass in kgs, so I'll just change this from kilo to newtons, so that now I have 17644. Now I have 937 newtons, and this will be divided by 9.8 by 0.79. So this comes out as, we have 2,279, that's 2,279,118.7 kgs. Okay, so this is what we have. We can convert this, or we can write it in scientific notation. That's kgs is fine, or you can write it in mega. Again, don't forget how you convert it to mega. I say 2.279 by 10 to the power, I'm moving this 1, 2, 3, 4, 5, 6 kilograms. Yeah, we can say 2.279 mega kgs. Okay, so yeah, basically this is how you find the mass of the car and the load. So of course here the assumption, I think this is fine, this works out. Okay, now guys, again, if this gets enough likes, then I'll move on to work out the next part. See you guys in the next one.